Up until now, we have been talking about taking an image, but that is devoid of color. We have seen that we can image grayscales as number of photons per unit time, but the world is not as boring as I'm making it seem in the last few videos, right? We see color, we see vibrant colors, we see the world in amazing color. The question is, how can we enable our robots to do the same? Let's dive right into it today. So the first question is, a lot of you who has ever used a color camera, who has a smartphone, taken a picture, you see that the colors are made up of red, green and blue. Even in our smartphones, we see that the colors of the LEDs of each pixel is red, green and blue. The question is, why specifically red, green and blue? Why not something else? Why not some weird color like violet? Why not something like yellow? Why not something like cyan? Why specifically these colors? The answer lies in a very simple phenomenon. It's more about how we as human beings perceive color and see color. So in our eyes, we basically have three kinds of cones: the blue cones, the green cones and the red cones. Cones are these cells which are hypersensitive to the color pigmentation in the light, and we have rods which are basically somewhere in the middle, and they are super sensitive to the intensity of light. Rods are what help us perceive things at night. They are super sensitive at low light. So that's why if you have observed at night, we actually don't perceive colors really well, right? But we can perceive what is going on. We can perceive this like in almost like a black and white grayscale movie. That's where rods are really active. And it's active at about 498 nanometers of light. And on the other times of the day, like in the mornings, we see color in vibrancy. We see blue, we see green, we see red, and we see a mixture of all these combinations of color. Essentially, color is different wavelength of light and how our brain is responding to these different wavelengths of light. Here on the left y-axis, you see that it's the amount of intensity we perceive, and on the x-axis we see different wavelengths of light, which is essentially different colors of light. Awesome. Let's take a smaller step into mathematically modeling these. I'm going to call the short wavelength of the blue one as S of lambda, the green wavelength or the middle wavelength as M of lambda, and the red wavelength as L of lambda. So this is just a representation for me to just say that, hey, I have one peak and it basically falls off in a different way. Remember that the S, M and L curves do not have to be exactly symmetric. As we saw before, they are not, right? But they peak at different frequency, different wavelengths and different frequencies, and they fall off at a different rate. So our eyes do not perceive red, green and blue at the same level. And this is exactly one of the reasons why certain colors actually like trigger certain emotions in our brain, and that's where this comes from. So now let's just imagine in the world there is some object which is emitting all colors of light. Again, this is represented by this black curve called f of lambda. To understand how we would perceive this as red, green and blue, we would need to look at a little bit of math. This is called the convolution operation. So the effective color in the red or the S region, you would see it as a convolution of the S filter with the F, the actual black curve, and same with the M, same with the L. You can essentially think of this as mapping an infinite dimensional color space, which is the black curve because it has every single value of color in the visible region, to just three values, which is red, green and blue. And that's one of the reasons we call these the primary colors, because as a weighted combination of red, green and blue, we can make up any color. So you can have a lot of red and the image will look more red. You can have a lot of green, the image will look more green. You can have a lot of blue and that will look more blue. If you add all the three colors at full intensity, that will look like white. If you like make all of the values dim, it will look like dark gray or black, right? And we can like play around with these sliders ever so slightly up and down. If you have ever opened like image processing program like Photoshop or Paint and you've played around with the color wheel, that's what I'm talking about here. Awesome. In the real world, we can have many entities with different kinds of curves. We saw f of lambda before, we can have a completely different curve which looks like this, right? This could be called f prime of lambda. The catch is that because we are perceiving only 3 values of color from this infinite dimensional color space, you can have f of lambda and f prime of lambda look completely different because of when you draw out the actual curve. But when you do the previous convolution step to get like s, m and l values, they might have the exact same values. And this can cause like us to perceive two different world quantities which are actually of different color to look like the same color, right? And depending on the way you perceive s, m and l, which varies from person to person and animal to animal, we might all see colors in a different way, right? My definition of green would be different from your definition of green versus your definition of blue, and so on. And I'll show you an example later on in a few seconds, which will be very intriguing and exciting to see. Let's take a side step. Let's look at this amazing animal called the mantis shrimp. The mantis shrimp is one of the most spectacular animals with its amazing vision. Remember that humans can see red, green, and blue, and anything which is like on the beyond side of blue is called ultraviolet, and we don't see that. And this is what we actually put sunscreen on to block so that it doesn't harm our skin. And we definitely do not see infrared, which our thermal cameras see, and which is beyond the red region, right? We do not see these colors. But the mantis shrimp, on the other hand, is so spectacular that it can actually see all the way from ultraviolet all the way to the infrared region, right? And it just doesn't see 3 colors, it sees a whole spectrum of 12 colors with the spectral sensitivity like we saw before shown here, right? And it's amazing what these animals can do with this kind of vision, right? And I promised to you that like I'm going to show you an example of what happens if we see colors slightly differently. On the left hand side here, you've seen this dress illusion wherein it went viral a couple of years ago, wherein the people were trying to argue and identify what color the dress actually was, right? The original image, according to the author itself, is basically blue and gold. Some people might see this as blue and gold, but some people might not. The left image is the questionable image, but hopefully most of you or all of you will see the middle image as white and gold, right? And hopefully almost all of you will see the right image as black and blue. What we have done here is we have changed and edited the image ever so slightly that our eyes across different people are more sure of which color it would be in the middle image and the right image. If it's still confusing, we still need to bump up the brightness and contrast like I've shown you on the bottom here, and hopefully at one point you will start seeing that. And it's so cool, isn't it, that like we thought colors are universal, but they're not. It's a figment and a perception of your own mind. The colors are all completely made up in your head, and we perceive colors very differently. Another amazing story is that the Himba people of northern Namibia, which is a tribe in northern Namibia, have a unique linguistic and perceptual understanding of color. They have such a unique perspective of color that their entire language has manifested in a way to reflect color. Especially the color green, they have multiple terms for different shades of green. We as human beings might, in the Western world or like the Eastern world, might say, hey, we have this light green, we have this dark green, we have this olive green, maybe like 5 or other 6 shades of green. But they have a lot of shades of green, but they do not have a separate word for the word blue, which is such an interesting thing. So they group blue with green. They might not be able to distinguish blue from green, but they are able to distinguish multiple shades of green, which we on the other side of the world might not be able to. So that's a very interesting and cool thing, how linguistics and language changes with the way we perceive something in the real world. You might wonder, why has this ever happened? Because the speculation is that the Himba people live around forests, so having different colors for green help them identify different herbs which are good for them, different bushes which are poisonous to them, and so on. And the color blue in nature is pretty rare, so it was not important enough for them to be able to come up with a word to distinguish blue, which is more common in man-made structures in the world we live in. So the question is now, if you want to make a color camera, how do we do that? One simple way is you say, hey, take a grayscale sensor, put a colored gel which only lets in one color of light. So you can do an image for red, change it to the green filter, take an image for green and put a blue filter, change it for blue, and so on. In theory, this would work, but the problem is this would be very, very, very slow, right? And this is what was done in the earlier 1940s, 1950s, where one of the first color cameras were there. They would have a disc which would like move around, and you would take 3 different images. The problem with that concept is that you cannot capture moving subjects, and everything has to be perfectly still because there was no computers to process this image at that point of time, right? So that's not that great. So in the modern day era, what we do is we utilize a concept called tiling, wherein we have on the gray thing you see on the left, you see like these different pixels which are in squares, and you'll see the colored filter which goes on the top, right? You'll see like for every 2x2 grid, there are 2 green pixels because green is the average color channel a human being sees. So green is pretty prominent, and you'll see one red value and one blue value, right? And so wherever that color is there, only that color dye is there, only that color is perceived, and the other colors are not perceived, right? And you will see this resulting pattern as it's shown on the right hand side there, and which is cool. And this entire thing is called a color filter array, or this specific pattern is called the Bayer pattern. And Bayer pattern is one of the most common patterns used for capturing RGB color. So let's look at another example. This is an image from Wikipedia. So you see that one is basically the original image, which would be perfectly captured if we were doing this with the first example we talked about with the rotating discs. 2 is basically capturing only one of the color channels, let's say red. This is showing you the red intensity. And 3 is basically when we take this intensity for each red, green, and blue and color it appropriately with the color. That's what 3 looks like. And in 4, remember that like we are missing colors in the alternating pixels. When we sort of like blend them together and interpolate them, which we will study in one of the later videos, how we interpolate these things, we will actually get a decent looking image in 4, but it has a bunch of like artifacts as you would see near the red colored rows. So we can take that, we can smooth out the noise and remove a little bit of this artifact, and you will see that the image in 5 is pretty close to 1, but it's not as sharp because we have lost a little bit of detail by doing this alternating pattern. So that's a pretty cool way to do this. And these are the kind of technologies which are used in today's day and era, which are pretty cheap, and they work relatively well. As long as we have a lot of pixels, this works really well. In modern day cameras, we have this thing called the sub-pixel level, wherein each pixel itself is divided into like a Bayer pattern, wherein it can capture multiple colors per pixel, and it works wonderfully well. Like I said before, the general idea is a color filter array. We picked the Bayer pattern like it's shown on the top left, but you could have any other pattern. Here, white pixel means that it's completely transparent, and it is super useful for getting information at low light pixels, right? And like depending on the scenario and depending on the manufacturer, you might see a different kind of a color filter array pattern as it's shown here. One simple example is shown on the right here. The Canon IXS PowerShot camera used cyan, yellow, green, and magenta, which is more closer to how the printers work. So this camera was like alluded for like capturing real good color for printing photos, so it was much better for that, right? And if you look at the CyberShot, it uses the red, green, blue, and cyan again, which is an interesting color combination. A lot of these are like choices made by the manufacturers for their design reasons, right? If you were to design your own color filter array, how would you do it? How would you design your own color filter array? The answer is simple and not simple at the same time. It's simple in the sense that it depends on the task you're trying to do, but it's complicated in the way that like depending on the task, it's actually generally very hard to say, hey, this is what are the colors that's going to be the best for my scenario, right? If you have to detect something which is red in color, having a red color pixel is good. If you want to design something that is orange in color, having an orange color pixel might be good, and so on, right? What criteria would you consider? It again totally depends upon where you're going to be deploying this for. For example, if you're going to deploy this in like low light scenarios, where color is not as important, you would want to consider using a lot of transparent pixels to let in as much light as possible, because putting this color filter blocks like about 1/3 of the light, and that's not really good when you have very little light to go with. The way these colors are represented on the computer is you capture this like Bayer pattern image, and then you do this interpolation technique, and then you finally do something called as smoothing, right? That's called debayering, this entire process. What we will do is we'll take this and we will represent it as a 3-dimensional array. So it's m by n for the size of the grid of the pixels, the number of pixels itself. If you have a 100 by 100 pixel array, that's 100 by 100 pixels. And then you have like the red channel, green channel, and blue channel stacked on the third channel on the computer. So it's a 3-dimensional array. In this particular example, the pixel values are normalized between 0 and 1, but it doesn't have to be. It can be 8 bits, wherein the general idea is that it's value between 0 and 255. So like the black is 0 value and 255 is the white value, and you can have this for every single color channel. And like you can have 16 bits, which is 0 to 65,535, or you can have 24-bit depth, which is 0 to 16 million colors. And that's where the 16 million generally on our smartphones comes from. That's the color depth. Depending on how you interpret these colors, things can be very interesting. You can say like, I am going to value my red channel more, tone down my blue channel, and that might give you something like this shade color balance. You might say like, blue is very important to me, I'm going to bump up the blue value and drop down the red and green values, and that might look like the image on the tungsten image on the left side of the image. Depending on the way you interpret these red, green, and blue colors, you can get different feel for the color and different kind of color balance. These are super important to sort of make the white look neutral white and every other color look neutral, because when you're shooting into the sunset, you have too much orange. Maybe you would want to bring down the value of orange. If you're shooting in like a tungsten sort of scenario, you might want to add more blue to make it more neutral, because the color of the light itself is orange, right? And so on. So these are super cool. This is how the sensor basically blends together. This is what is called the pixel color science. Let's look at a simple example here. You have this image of a strawberry on a tray. The image looks a little weird. If you see it, you might be like, the image is abnormally cyan or blue looking. But if you like look at it for a few seconds, you start seeing the color on the strawberry. If I ask you what is the color of the strawberry, most of you might say that, hey, the strawberry looks like red. But what if I tell you that you can take a color picker or like read this into a computer? There is no pixel in this image where the red value is actually higher than the blue or the green value, which would be very interesting because that's what red is, right? But because on the back of the image we see a lot of cyan, our brain has added a lot of like red into this color. So whatever is neutral gray will actually appear red to us. And knowing the fact that this is a strawberry, we actually would see the strawberry as red in color, right? Again, that's called color constancy, wherein under different lightings, our brain would perceive the world in the same way, and it actually would make the colors look as it would naturally. This is another example where color constancy is not that great because we don't know what this is. I would like pause the video for a second and think what this is an image of. This is an image of a parachute. It's a parachute which is folded. Notice that the green and the blue and the red colors are the same as that in the background, but the background is in shadow, so the color looks completely different, right? But we want our computer algorithms to be able to like match the colors in a way that we know that it's the same color, which is again an interesting phenomenon. Another example of this would be the auto white balance feature on your smartphone or on your GoPro. If you have ever gone like deep sea diving, you know that the color of light changes pretty significantly with the depth of water. So it would actually be really, really hard, right? The image on the left is what you would see from a normal camera. The image on the right is what you would see from an awesome white balance method, right? Let's say you are a computer vision engineer in a company and you want to build this yourself. The question is, how would you do that? I want you to take a second, pause the video and think about it and come back. The answer is not that simple, because like you can't just say like I'm gonna have equal amount of yellow, equal amount of blue, equal amount of green, equal amount of red and so on, because how would you know what that is, right? So instead what we will do is we will resort to something which is known. This is called a color checker board or a color calibration target board, where it has perfectly printed with a very high accuracy printer different kinds of colors which we humans would perceive as the right color. You'll see different colors on the top 3 rows and you'll see different amount of gray levels on the bottom row. And you would take this, you would basically place this in the scene you're trying to image. You would take a picture, you would basically apply a color balance filter which would change the amount of red, green and blue in a way that this board in the image matches up pretty accurately with the image on the left. And that's how you would get a perfect color balance. In really expensive movie sets, this is what is actually done. Of course, in today's day and era, there are deep learning algorithms wherein you can make image pairs of like the correct white balance and like the raw image, and you can just like learn a neural network to be able to finally predict what the color balance should look like. So here is a real world example of something called Google Pixel's Real Tone, which is on the Pixel smartphones. If you just take a dark skinned person and try to color balance them, what would happen is it would artificially brighten the person's face, which is not flattering at all, because you're artificially changing the way the person looks, and you're putting like these biases into the society that like a certain kind of skin tone is actually better, right? We don't want to be doing that. So, but Google, these products actually work really well, wherein they work well with nuanced white balances. The question is, how does Google do that? What do you guys think? So the idea is that Google collected a lot of data with a lot of people with different skin tones, and they basically had an expert basically come and like modify these like images in a way that would look natural to that person and accentuate their beauty, rather than making them overly like look like a specific color, right? So what Google in their Pixel smartphone does is it essentially detects the subject, it takes their skin tone and it applies a different filter for the skin tone than the background itself, right? And it's a very beautiful nuanced way of doing these like really intricate white balance kind of things. So just to understand, we learned about what is the use of RGB and how we see as humans see color, how is RGB captured, why is mantis shrimp amazing, what is color constancy, and how you could perform color balance. Now you have the power of color, use it and make the world a colorful place. See you next time. Bye.